Hello everybody, and welcome back to another CIV 398 assignment guide. So in this assignment guide, we're going to be covering question 1 of assignment 5, and it's really nice for us because the question is nice and simple. It's a great way to kind of get into the assignment spirit and start the assignment. So let's get into it. So question 1 says, the shown cuboid, I don't even know how to say that, but you guys know what it means, and you guys have a picture of it, of course, so in case you don't know what it means, there's a picture, and I'll be showing that picture on the next slide. It says that it is under a state of stress shown by the Cauchy stress matrix below. So we see that we have a nice symmetric stress matrix, very typical. We see there's only one negative component, which is sigma 2, 2. Not too bad. And it says the coordinates of points C, B, and D are given. So, of course, on your guys' figure or in the text, you guys will be given the coordinate points of points C, B, and D. And it says the cuboid is composed of two halves glued together on the plane ABCD. So if we look at this cube, it actually looks like two wedges glued together. So that's going to kind of be the key moving forward. And the question is, this isn't a cuboid, it's actually two wedges glued together. And it says the maximum shear stress and the maximum normal stress the glue can take is 100 MPa and 200 MPa respectively. And the question wants us to determine three different things. The first one is the normal stress on plane ABCD, and the second one is the shear stress on plane ABCD. And this is really nice because once we have the normal stress and the shear stress, we can compare those to the limits given in the question. So it says that the maximum shear stress is 100 MPa and the maximum normal stress is 200 MPa. So once we get our normal stress and our shear stress, we can compare them to those limits, and then we can answer part C, which says, does the glue fail in tension or fail in shear? So if they both exceed those limits, then it fails in both tension and shear. If it just exceeds it in shear but doesn't fail in tension, then it just fails in shear, etc. So it's not too bad. The key here is getting the normal stress and the shear stress. So let's talk about the stress at a point. So this is the same slide as before because it applies again, and as you guys will see, it's not too bad. So if we take a point and cut it, well, that cut is going to be defined by a normal vector. So this normal vector, even though it's not very clearly shown, this is perpendicular to that plane. And with that normal vector, we can start deriving a bunch of things. And the first one, which is going to be the key, is called the traction vector. And our traction vector is going to be our Cauchy stress matrix sigma multiplied by that normal vector. And again, that traction vector is more or less the internal stresses of that point. Remember when we cut a beam in Eng 130, we had the internal forces of shear and bending moments? Well, now when we're cutting this point, we have those internal stresses that we have to deal with. And what we can do with these stresses, and we can define them as two different stresses. The first one is the normal stress. So this is the component of that traction vector that is parallel with our unit vector n. So as we can see from the picture here, our red arrow or red vector, which is our normal stress, this follows the same path as our unit vector. And how do we find that? Well, we take our traction vector Tn and we dot it. So we don't multiply it, we dot it with our unit vector n. So all we have to do once we have our traction vector is we just dot it with our normal vector, and then we have our normal stress sigma n. And the second component obviously is going to be the one that's perpendicular to that normal vector. As we can see from the picture below, we have the nice green vector, and this one's perpendicular to that normal vector. And this is called the shear stress. And tau is equal to the norm, so this isn't the absolute value. Remember, when we have two of those, I don't know, straight lines, vertical lines, I don't know the proper name for them, but if we have two of them, this means the norm. So we look inside of that. We want to take the norm of our traction vector Tn minus our normal stress. So here's kind of the first trick. Inside there is sigma n. It's not sigma, it's not a matrix, it's sigma n, which is our normal stress, which is just going to be a scalar as we'll see above. And we take that normal stress and we multiply it by our normal vector. So as we can see, looking at our traction vector, it's going to end up being a vector because we're taking a 3x3 matrix, multiplying it by a 3x1 vector. That, of course, is going to give us a vector. Now, if we look at the normal stress, sigma n, we're taking Tn, which is a vector, our traction vector, and we're dotting it with the normal vector. So if we dot two vectors together, that's just going to give us a scalar value. And finally, at the end, we look at our shear stress. Well, we're taking our traction vector minusing a scalar times another vector. That's going to give us a vector. But then we're taking the norm of this vector. And of course, the norm of a vector is simply a scalar. So those are kind of some things to keep in mind. If you're calculating your shear stress and you get a vector, well, something's a little off. So we're going to have to figure that out in case that happens. All right. So as we've seen from the previous slides, it's pretty easy to solve this question to find the normal stress as well as the shear stress if we have that normal vector. However, the question doesn't give us what that normal vector is. So we're going to have to figure out what exactly that normal vector is. So let's take a look at a cuboid. I still don't know if I'm saying that right. And let's take a look at what we're given. So the question gives us three things, three different coordinate points. So we know point B, point C, and point D. And we have to ask ourselves, what can we do with these points? And now I know it's going to be really difficult, but we're going to have to think back to N130. And remember N130, if we had coordinate points, we can find the vector between those 2 points. And that's exactly what we're going to do. So if we look at these 3 points, we can create 2 vectors between them. The first one is the vector that goes from C to D, and the second one is the vector that goes from C to B. So we can create 2 vectors from these 3 points. You say, Clayton, well, N130 is a long time ago. I forget how to do that. Well, it's actually very simple. So if I want the position vector from point C to point B, all I do is take the coordinate point to B and minus the coordinate point to C. You're taking the coordinate point of where you end up and you're subtracting it from the coordinate point at which you started. So if I wanted, again, the coordinate point from C to D, I'm going from C to B, so I'm taking coordinate point of B minus the coordinate point of C. And saying, okay, Clayton, well, now I got these 2 vectors. What's so special about them? Well, if I were to find a vector that is perpendicular to both of these vectors, it'd be in the direction as so, n. And say, well, hold on a second. If the 2 vectors are in the ABCD plane, well, then that vector perpendicular, well, that's going to be our normal vector. Well, so this is great. So if I have these 2 vectors, all I need to do is find a vector that's perpendicular to both of them. How do I do that? Well, we use the cross product. As you guys remember, the cross product returns us with a vector that is perpendicular to both of the vectors we cross. So in this case, our normal vector n is just simply going to be the vector RCD cross, so not multiplied, but cross RCB. And I know that a lot of people will do this. It's going to be nice and easy. They're going to get their vector and they're going to move on, and then they're going to message me and say, Clayton, what the hell? I did exactly what you said. I got the wrong answer. So remember this one little trick. Here's the final trick to the question. Our normal vector needs to be normalized. If you guys do not normalize this normal vector once you obtain it, you guys will get the answer wrong. So there's kind of the final hint. Normalize this normal vector, and of course, once you have the normal vector, everything else is nice and smooth sailing from there. So that's it. That's question 1. As you guys will see, it's not too bad. It's basically 4 steps. Find the position vector, find the normal vector, find the shear stress, find the normal stress. Or I guess you'd find the normal stress before the shear stress, but whatever works for you. So that's question 1. Thank you guys so much for listening. I will see you guys in question number 2.